types of bonding. What are those? Okay, so metallic and ionic are actually the least important ones, but yes, they are important. Covalent, yeah. So the metallic and ionic, you don't ever have to really worry about polarity. So yeah, you know that it's always going to be an electrostatic force. So always you don't even have to worry about bonding or polarity because it's always an electrostatic force that is involved here. In metallic, it's the electrostatic force between the negative electrons that are free to move and the positive kernel. So you've got the positive kernels, and then you've got these electrons. I should have used another color, doesn't matter now. You've got these electrons that are then free to move and conduct electricity. Okay, so it's an electrostatic force between the delocalized electrons and the positive kernels. Electrostatic is always between positive and negative. So if you see electrostatic, you know it's positive and negative. So for ionic as well, it's not atoms, it's not molecules, it's ions. Sorry, terrible. No, I also haven't really spoken today, so you've got the positive and the negative, positive and negative. And remember, it also goes in the other direction. So, all surrounding this positive, there will be many negatives. And surrounding this negative, there will be many positives because it goes in all dimensions. And that is why this is such a strong force and why they're normally solids because they are not free to move. These are then ions, and again, it's an electrostatic force between a positive and a negative. Oh, yo, how do I write there? So it's between the ions, and the ions then have the electrostatic force between them. And then when you want them to conduct, you have to melt or dissolve them. So, yeah, sure. This is going to be a husky for the rest of my life. So, yeah, it's always going to be the ions then. Okay, so yeah, no polarity because it's positive and negative stuff. They permanently positive and negative. So you don't have to worry about polarity there because they charged. They permanently charged. It's in the covalent ones where we have to worry. So only for covalent you have to worry about that. So now in covalent also, please remember the new sags. Are you there? Okay. In the new sags, the covalent is the only one that has intramolecular bonds. Only one, not the other two. We're not allowed to say that metallic and ionic is intramolecular anymore. And your exam is going to be based on the new sags. Did they say that to you? Okay, good. I know they looked at the new sags very detailed. So when you see intramolecular, I always say the A must lead you to atoms because it's a intramolecular bond. So when you see the word bond and it's intramolecular, then you know it's only between two atoms at a time. And don't think about the molecule at all when you see bond. It's just about two atoms and what they are doing to bond with each other. So if you look at, and now normally it's, so you're not allowed to say always anymore. So it's between two nonmetals. So, but that's not the definition. The definition is still that one atom will take its electron and move it to another atom. Or I'm just giving it a charge already. Move it to another atom. So when they don't have a charge, we still call them atoms. So now, not move, share. Oh, that's actually very wrong. I shouldn't draw an arrow because if you draw an arrow, we mark it wrong. So it's atoms, and one atom will share its electrons with another atom. So when you do the arrow, it will be here, where one atom moves its electron to the other one, and the one becomes positive and the other becomes negative. That's a ionic bond. But when you so there you don't have to worry about polarity. But now, yeah, this is still an atom and that is still an atom, but they're sharing electrons. And this new thing that we're forming is now called the molecule. And that's the only time when it's called a molecule. These things are not called molecules. It's only this one that is now called a molecule. And that is why this is the only one where we can say intramolecular, because it's the only one that forms a molecule. Okay. Now, it all depends on the electronegativity. So now you have to go to your periodic table and you have to go and look at the difference in electronegativity. This is for bonding, not for molecules, for bonding only. You look at the difference in electronegativity. So if it's and if the difference in electronegativity is zero, okay, then we're gonna, I'll do an example now. Then we're gonna say it's gonna be a non-polar. But you don't just say non-polar. Use three words because otherwise you're not gonna get the mark. You have to say non-polar, covalent, and that's not even enough. Bond. Make sure you use three words. Non-polar covalent bond. You're never going to say it any other way. Um, Even if you're tempted to, don't, because maybe sometimes it doesn't count. They don't want non-polar, or but just be safe and put it there so that you know you're getting the marks. Because they should be saying specific, but in the matric paper, they don't always say specific. So just get used to saying if the electronegativity difference is zero, you always just say non-polar polar covalent bond. But then if the difference in electronegativity is not zero, and we'll do an example of that as well, then we're going to say that it's a polar covalent bond. Again, please write all three words, polar covalent bond, because then they know you know what you're doing and you know it's a bond. Because as soon as you say force when you're supposed to say bond, we don't mark any further. We just stop marking and you don't get marks. When is your test on this? Okay. Hmm. Okay, so what I don't, I'm sure they've shared last year's tests with you already. So maybe we must try and work through one of those tests if we have time on bonding, that you see how it gets asked. I actually have two tests now because my grade 11s and my grade 10s wrote a test on it. So I can actually send both of those to you. Okay, so now let's just look at examples of that before we go to the molecule. So if I have something like, do you have a periodic table with you? Okay, then you can actually look for the electronegativities. Is it close? Okay, so if you have something like, okay, so if they say, what are the bonds like in all the diatomics? H2, Cl2, you know all the diatomics, right? I2, any of the diatomics. Then if you look at one H, what is the electronegativity of an H? Correct. And then you know a hydrogen only has one electron, and then the other hydrogen will also have an electron to share. And then what is the electronegativity of this hydrogen? Also 2.1. So is there any of those that's winning? No. So these electrons are going to live here in the middle. They're not going to move over to the hydrogen or to the hydrogen side. They're going to stay exactly in the middle. And that is when we call this a non-polar covalent bond. Because if you take 2.1 minus 2.1, you get zero. And that is what we said here. We said if the electronegativity is zero, then it's a non-polar covalent bond. Okay, but it doesn't always have to be the same atom. You can get something like pH4, pH3, sorry, pH3. Now, if you look at pH3, don't get confused with the molecule because if we draw that molecule, how many electrons will P have? Valence electrons. Sorry? Five, yes. So we're going to say one, two, three, four, five. So now you can see it's got three that it would like to share. And we know that hydrogen already, we did it here. So hydrogen's only going to share one. So hydrogen will share one there, hydrogen will share one there, and hydrogen will share one here. But now if they ask you about the bond, what are you going to look at? See, this is where people get confused because you're thinking too far ahead. If you see the word bond, remember what we just said. You're only going to look at two atoms at a time, and you don't care about anything else. You only care about the. This is very wrong. I just saw it now. The, I said electronegativity zero and electronegativity zero. This one should be not zero. Okay, so electronegativity here must not be zero. Now, so that's all you care about. You're just caring about two atoms at a time, and you worry about is the electronegativity zero or is the electronegativity not zero? And that's what and you don't make it more complicated. So all you're going to do is you're going to look at two atoms at a time. So you take the P and one P, one H, because they're asking you for a bond, and we're only going to look then at one atom, or at two atoms. So we're going to just worry about what happens between the H and the P. So tell me what's the electronegativity of the H and P. So what's the difference in electronegativity? Great. I'm not going to write it all out. Non-polar covalent bond. Yes. So please don't think further than that. When you see the word bond, you should know, keep it simple. It's only going to be between two atoms at a time. So here again, if you look at this side, let's just do another color here. If I now look at this bond between P and this H, that's a different bond. So between P and this H, what is that bond going to be like? It's the same. So it's also going to be a non-polar covalent bond. And I'm going to get back to this molecule later when we look at the molecules. You can see it's not the bond in the molecule actually has nothing to do with each other most of the time. Okay, so to decide on the bond, you don't care about what the molecule looks like. You just care about what this relationship is between two of those atoms at a time. Okay, so that's non-polar. If we go to polar, uh, yeah, so polar covalent. So it's still a bond. So if the question asks about bond, you know you're going to look at only two atoms. So let's now go and find something. So if we say we've got HCl, for instance, and we've got, let's do CH4, because I like asking those. So if I look at HCl, again, how many electrons will hydrogen have? Only the one. And Cl? Yeah. So you can see they want to share only these two. Okay. So that's the bond that they're going to form. That's the covalent bond because they are sharing electrons. So now, again, if they ask you about polar covalent bond, what are you going to do? Two atoms, and you look at the electronegativity. So now tell me again, what is hydrogen and chlorine? And which one wins? Okay, so now we have what we call a dipole moment. We have the electrons wanting to move over to the Cl side. So when I look at the molecule, the electrons will be sitting more on the Cl side. So are they still sharing those electrons evenly? No, the Cl is winning. So that means when I look at my difference in electronegativity now, it's 3 minus 2.1, which is zero point 0.9. Is it 0? Okay, so it's not equal to 0. And when it's not equal to 0, I know this is where I'm going to go. Not equal to 0, so it's going to be a polar covalent bond. Okay, so that's what you're going to write. It's a polar covalent bond. Okay, now we've got CH4. Okay, so tell me about CH4. How many electrons does C have? 4. So I'm going to have a C, 1, 2, 3, 4. And then we've got hydrogen that can share. I'm not going to draw it separately. You know now that hydrogen can share 1. So there's going to be a hydrogen there. There's going to be a hydrogen there, hydrogen there, hydrogen there. Okay, now we're going to say, okay, they're asking me what type of bond it is. So what am I going to look for? The two atoms. Yes, then they must be. Then they must, because normally when they ask you about the bond and the polarity of the bond, they would say it would only be two. If there's more than two, they will have to say what's the CH bond polarity or what is the CF bond polarity. We can do one like that now. Yeah, I actually should do one like that as well. So if we look at this one though, we're only going to look at one C and one H at the time. So what is H again? And C. Okay, so again, this is going to be a. So to get the electronegativity difference, you're just going to say 2.5 minus 2.1. It's absolute value, so always the biggest minus the smallest, and that gives you zero point 0.4. And is it 0? So what do you know? Are you allowed to just say that? Please. Because why I want you to get used to that is when it gets to molecules, you can't just say polar and polar all the time because it's different when it's a polar covalent bond and when it's a polar molecule. So that is where you have to be why you have to be very specific, and it helps you with your thinking as well. Anyway, but now, like you said, it could be a molecule where let's do this. I don't even know if this exists, but it does not really matter. So if I say I've got a molecule like BCl2H, okay, I don't know if it exists, but it really doesn't matter. Now I wrote everywhere where I want to draw. So if I have that molecule, okay, so again, how many electrons? So often they don't ask you to draw this, but it's just once you've drawn it, and it's actually quick, then it makes your life so much easier to go and think about what's going on. So an Lewis structure is quick to draw. Then you can see here's a space for a hydrogen because we know hydrogen shares only one, and then we know Cl has 7. We did it already, and we know that that is also going to share one, so it will still have its own little electrons here and another Cl will share here, and it will still have its own little electrons here. Okay, so now the question asks you again about that. Now they have to say, so they will say, explain the nature of the PCl bond, or they will say, explain the nature of the pH bond. They have to be specific now. So now, if they ask us about the PCl bond, what are you going to do? It doesn't matter, but only two atoms at a time. So so this PCl bond is going to be exactly the same as this PCl bond. So it doesn't matter which one you look at because they're going to be the same because it's between P and Cl, only two atoms at a time. So if we look at the P, what's the electronegativity there? 3.1 and, oh, sorry, 2.1. Is that P? That's P. P is 2.1 and Cl 3. Okay, so the difference in so if we look at this bond, we can see that the difference in electronegativity is zero point 0.9. So is it zero? So what are you going to say? One, one nonpolar. It's not zero, yeah. So it's a polar covalent bond. But now if we look at the other one, if we look at P and H, okay, so this one will be exactly the same. So here between P and Cl, it will also be zero point 0.9 and it will also be a polar covalent bond. But now if we look at this one, the P and the H, now what goes on? So again, we're going to look at the difference in electronegativity. So tell me, what is P and H? And now what's the difference in electronegativity? So what's that bond like? It is zero this time, yes. It's a non-polar covalent bond. Yes, not say the whole thing, non-polar covalent bond. Okay. So are you okay with the bonding thing? So in one molecule, you can have bonds that are polar, and then you can have other bonds that are non-polar, because you only look at two atoms at a time. Okay. So that's the bond part. But then they move on and they now confuse you because now they go to molecules. And now you need to remember, if it's molecules, molecules can only form when it was covalent. Remember, we said that then. So only covalent bonds will form a molecule. Okay. Only. Very important. So if it's ionic and metallic, you don't care about molecules. Are you still with me? It's okay. So if it's the other two, you don't care about molecules. It's only when it's covalent. And now you look at now you have to look at the shape of the molecule, because now it's not only the electronegativity that matters when you decide, is the molecule polar or non-polar. So you have to look at the shape. If the shape is symmetrical, I can never spell that. Symmetrical, then you know everything is shared out evenly. And then when the electrons are spread out evenly, everything is spread out evenly. Then you know it's going to be a non-polar. Can you just say non-polar? You have to say non-polar molecule. So just teach yourself that you're never going to use the word polar and non-polar on its own. Just say nonpolar molecule or nonpolar covalent bond, or or polar molecule or polar covalent bond. Always like that. Otherwise, you're going to get yourself confused. So nonpolar will be if it's symmetric. Oh, that should be a Y. Hey, if it's not symmetrical, so it doesn't matter how it ends up being not symmetrical. We'll look at examples now again. If it's not symmetrical, oops, symmetrical, yeah, symmetrical, then we know we've got a polar molecule. You have to say the whole word. Okay, so let's see now. So if I go and I say, fine, I can go back to my molecules that I had before. Let's just look at H2 again. So H2 was sharing one electron, right? So that's the molecule we had. We said that this bond was a non-polar covalent bond, but now we don't care about that because now I'm asking you about the molecule polarity. So if I ask you about the molecule polarity, what do you look at? Polarity, yeah. What do you look at? Shape, the symmetry. Yeah. So if you look at this one, is there any side We know already that these electrons live in the middle. So is there any side of this molecule that is more positive or negative than the other? No. So what will we call this molecule? A non-polar molecule, yes, because there's no side that's more negative than the other. But if we look now, that's all. It doesn't always have to be two. We can also look at our CH4. So if we look at our CH4, remember C was sharing the four electrons with hydrogen. So it looked like that. Now I ask you again about the molecule polarity. Okay. Can you just say nonpolar? Nonpolar what? I'm going to drill it into you. Nonpolar molecule. Yes. Okay, and this is important when you go on to the intermolecular forces. Once you can decide if it's polar or non-polar, your life becomes super easy. Okay, so let's look at the P one. So P was like this. It had five, you said, two, three, four, five. It doesn't matter where you draw the two on its own, and it was sharing with H and sharing with H and sharing with H. Okay, so there's our pH 3. Now, if I look at this molecule, they don't really ask you pH 3 anymore because they were fighting about it and then they just took it out of the syllabus. But it's still a nice one to use as an example because you now know that when we look at the bond, it was 2.1, 2.1, 2.1. So the bonds were non-polar covalent bonds. But now, if we look at the molecule, are the electrons evenly spread out now? Yeah. Does mess with stuff. It actually messes with stuff before the H's even get there. And that's what people don't always understand. Because if you have here, these electrons here are two negatives. Then you've got an electron here that's one negative. And you've got an electron here that's one negative. An electron here that's one negative. Now remember, negatives repel each other. If it was 1, 1, 1, 1, they would repel each other evenly. But now here, I've got a stronger negative force. So these electrons that are wanting to share with something is being pushed down by this stronger negative force, not even electronegativity, stronger force because they're repelling. Electrons repel. So two electrons are going to repel more than one electron. So they're already pushing these electrons down before this atom has even decided to share electrons. And that is why you get this pyramidal shape. Do they make you learn the shape still? Okay. So this is then you can see it forms a pyramid. Okay, so that's your trigonal pyramidal. Trigonal just means three, pyramidal shape. And so that happens before the H's are even there. And that is why this side. So then an H comes here, in here, and share, and share, and share. Okay, but they already were pushed down. So that means that this side of our molecule is now more negative than this side. So we say that this is a delta negative side, a delta negative just because it's a little bit negative. And this side of my molecule is delta positive. So that means that this molecule is not symmetrical anymore. So what are we going to call this molecule? A polar molecule. And we also call a polar molecule a dipole because a dipole means it's got two poles. It's got a negative pole and a positive pole. So we call it a dipole. Okay, let's just look at another one. So if we take the Cl4 again, CH4 again, and instead of having the H there, we put a Cl there. So that Cl is sharing one electron, but it still has its own electrons there. Now this molecule still wants to be, the shape is the same. It's still tetrahedral. So the shape is still the same, but now we need to look is if I look at this whole molecule, is it still symmetrical? No. So which side is going to be more negative? Yeah, because it's got those electrons, but also if you look at, okay, I don't really want to look at electronegativity, but the Cl will pull those electrons more. But yes, there are plenty electrons there. So this side here is going to be a little bit more negative, and this side there will become a little bit more positive. So what will I call this molecule? Now it's a polar molecule because it's not symmetrical anymore. Okay. And then once you decide if it's polar or non-polar, then can you worry about the intermolecular forces. And it's only molecules that can have intermolecular forces. When you work with ionic and metallic, you're not allowed to say intermolecular forces at all. My grade 10s were so confused. They kept on, when we ask about the metallic and ionic, why they have high boiling points, they keep on saying these high intermolecular forces. Are there intermolecular forces in ionic and metallic? Yes, because they're electrostatic forces. There's no IMF because they don't form molecules. But for covalent, there are IMFs keeping them together. And you've done the intermolecular forces, right? Okay. So should we quickly look at them? Or is there any questions in the book that you want to look at rather? Okay. So let's look at now how we decide about the intermolecular force. Because it's a molecule, you need to look at the molecule. And you look is at the molecule symmetry. That's all you have to look at because you are looking at intermolecular force. So what if we find, I'm going to just do a general one again and then we can look at examples. If we look at a molecule that is symmetrical, so if you say yes, the molecule is symmetrical, then is there any side that can be polar or that's more negative than the other? No. So what will you call this molecule? Which one? It's symmetrical. Is there a pole? No. So if your answer is no, then it is there's no pole. Okay, that you're not going to say. There's no pole, so it is non-polar molecule. But when your molecule is not evenly spread out and it has a delta negative and a delta positive already, then what am I going to call the molecule? A polar molecule. And a polar molecule will always be a dipole because it's got two poles. Okay, so when it's not symmetrical, it's going to be a polar molecule. When it's symmetrical, it's going to be a non-polar molecule. Okay, when it's a non-polar molecule, your life becomes super easy because we always, and we'll look at how they form now, but we will always, if it's a non-polar molecule, it's always going to be London IMF. Okay, remember if you in an exam, if you had said this once, if you once said that intermolecular force is IMF and you write it out once, then you can, for the rest of the intermolecular force, if you've written it out once, you don't have to write it again. You can just use IMF. It just saves a lot of time. So now if you, so it's always, that's the nice thing about it. As soon as you've established that it's non-polar, immediately you can say it's London IMF. But when it's non-polar, there are two options. Actually one, but the one is a special one. So the two options, because it's a dipole, it's going to be one dipole attracting another dipole. So that's going to be your dipole-dipole. And don't ever just say dipole-dipole either. It's a dipole-dipole IMF or don't say London, it's London IMF. But oh, you're not there yet. Okay, I must actually look. Let's look at your book. Okay, let me quickly look if you in that chapter is if there is even IMF. I did open the chapter here. Maybe they decided that they're not doing IMFs with you this year. Um, that was chapter 3. Hey, oh, chapter 3 is covalent bonding and intermolecular forces. You weren't absent, eh? I'll tell you now which page. Oh no, this is a Word document. I'm opening it. Oh, it doesn't matter. It should be in your book on page 3, from page 316 onwards. Or maybe this is the old version of the notes. I'm going to quickly look in the other notes because I did make a folder for 2023. Yeah, so you stopped before intermolecular forces. That's weird. Okay, then we don't have to do that. Maybe you must check with them because yeah, I've got the okay. So yeah, it's definitely past that. Can you see that it's there though? So yeah, it goes iron dipole and then it gets van der Waals forces dipole dipole. Yeah, it is in your book. So will you check with them if you have to do it or not? Because then we don't have to worry about them now. But then we can. But once you can decide the molecule symmetry, then it's easy. So let's just practice some of that. Or is there an exercise in the book that you want us to do that you struggled with? Okay, so I'll just make up some. Or actually, let me open this test that my uh, kids did. Hmm. We can just look at some of questions that you haven't got in your book, at least. I'm just opening it quickly. Yeah, see, but you wouldn't have anything about melting points and boiling points then. You haven't done anything like that, hey? So that's before that, yeah. Were you absent though? Otherwise, I'll just find a question that doesn't have anything of that in it. What were the answers? And what were the answers of that exercise? Did it ask you about ball boil? What did they sound like? Nothing about boil. Okay. Okay. Yeah. That's yeah. Then I wonder why. So weird. They must have made some decision that you're not doing the intermolecular forces now, which is I don't know. It feels as if it follows on each other, but it doesn't matter. Have you done the giant covalent bonding, like diamond, graphite? Okay, so that's the one thing I left kind of out, but but you don't need that really now so much until you go to. Oh man, am I doing copying the same thing? Okay, so let's just look at a few of these. I can also make questions up with the substances here. It's fine. Okay, so what they love doing is they give you a list of substances and then they ask you all kinds of questions about the substances. Okay, so I didn't even have to look at the question. So if you look at these, if you look at a list of substances like that, the first thing you have to do is tell yourself which ones are ionic, which ones are covalent, and which one are ionic and metallic and giants, because they are not going to be molecules. So you don't ever have to worry about intermolecular forces or polarity or anything with them. So if you look at these ones, which one will be a metallic bonding? It's normally something on its own. So you would know, yeah, Ne is on its own, but what is neon? Where is it in the periodic table? Very right. What things are there? On the very, very right. What is the last column called? The last group. Yeah. So they are noble gases. So do they bond with anything? No. So they will remain as atoms always. Because they don't want to bond with anything. They will always remain atoms. They don't form molecules. Okay, so please remember that. Yeah, noble gases think they're too good for all the other elements. And then, what is nitrogen, a metal or a non-metal? Okay, you must just look about at the metals that you actually know. I'm just gonna get a periodic table for us quickly. I'm just gonna draw it, rough one. Okay, so if I have the periodic table like this, okay, it's very ugly, I know. But if you look at the furthest metal that you're gonna find here is aluminium. So I always say go to aluminium to help you. Because if you put an aluminium roof on aluminium, you put a roof on aluminium, and then you go down like this. Okay. Aluminium is on this side. And then you'll see, yeah, also you have copper here somewhere, and you have gold here somewhere, and you have silver here somewhere, and those you know are metals. So the metals are on this side. But actually, if you do that thing there, you'll see that hydrogen actually belongs on this side. So hydrogen and all these things on this side will be nonmetals. Okay, so just look for things that you know for sure are metals. So that means that nitrogen is actually sitting here somewhere, and Cl is sitting here somewhere. So they are both nonmetals. So that's not going to be our ionic one. But we're still looking for another one that's just a metal on its own. Mm-mm. Oh, is it small? Can you not see? Okay, when it's a metal, it will just be one thing on its own. So the only thing that was one thing on its own is neon. Ooh, they put an S at neon. It's a solid. That's impossible. It had to be a gas. I only saw that now. Yeah, it's a gas. So G is a gas, S is a solid, and then you've got AQ. AQ means it's dissolved in water. Those are the three that we have: solid, liquid, gas, the normal phases, and then AQ. So it's actually four. Now, if you yeah, so this one is a solid, and it's on its own. That helps you to spot that it's a metal. Okay, so that will be a metallic bond, and noble gas will just have atoms. Then you can go and look, oh, the ones that are diatomic, these ones, always know is going to be covalent, and you always know that it's going to be pure or non-polar covalent. So you can immediately mark them as well as pure or non-polar covalent. Always, always, always covalent, and they're always going to be non-polar covalent bonds because they always going to be the same electronegativity. So electronegativity difference is always going to be zero. So they are actually the easy ones. So you know they are non-polar covalent immediately. So you know they are molecules. Okay, then we're looking for something that has a metal and a non-metal. H is not a metal. Mm. So HCl is covalent. Mhm. If they're both non-metals, 90% of the time it's still going to be covalent because they're just going to be sharing electrons. So all the metal, non-metal, non-metal is going to be covalent because they are sharing electrons. Okay, so always, so those, and HF is also one like that. So HF is also covalent because it's sharing electrons. Now, there's something special about SiO2. And those are remember, there are only three of them. And so that's why they should shout out at you. So SiO, it's silicon dioxide and graphite and diamond. Those three are giants. Yeah. But you must still say giant covalent. It isn't there. As neither is graphite, it's just carbon. So in diamond, it's just carbon atoms that are forming a huge carbon lattice. So they form a giant covalent lattice. And when we have to melt them, that you didn't really do yet, we have to go and break these pure covalent bonds, the non-polar covalent bonds. So the whole diamond is one molecule. So if you look at a diamond, the whole thing is one molecule, and that's why we call it a giant covalent molecule. Graphite forms layers. So you also have carbon, and then carbon in layers, in like flat table type thing. And then underneath it, you'll have another layer of carbon, and so on. Okay. So, and then they have layers in between with one valence electron that can move here in the layers. And that's why graphite is our only non-metal that can conduct electricity because it's got these layers. And so this is one big molecule and this is one big molecule. So it's still called a giant covalent structure because it's still one huge layer and another huge layer. And these electrons can move between the layers. Okay, so those are the three giants that we expect you to know. So that you can when you see them, just circle them immediately: diamond, graphite, and silicon dioxide. Silicon dioxide is glass in real life, so it's just glass, and it's a giant. But don't just say giant, giant covalent structure. Okay. Then we've only got a few, then we've only got one left. What is this then going to be? What's K? I don't know, lots of people do. Calcium is Ca. What is K? Yeah, yeah, potassium sulfide, yes. So, so yeah, potassium sulfide is going to be, is it, tell me what it's going to be. Hmm. Yes. So when it's a metal and a non-metal, 90% of the time, they're going to transfer electrons. If they transfer electrons, what type of bond is it? It is wrong because covalent is always sharing, sharing, sharing. Co- No, it's ionic. Whenever there's a transfer of electrons, it means the K gave its electrons to the S. So because the K gives electrons to the S, the K becomes K plus, and it actually will take another K and another electron, then the S will become S2 minus. And now you've got a positive ion, a cation, and a negative ion. When you have a positive thing and a negative thing, what is the force between them? Mm. What do we call the force here? That's okay. Ele- yes. Electrostatic force between them. So you don't have to worry about molecules here because there's an electrostatic. Also for metallic, it's electrostatic, so you don't have to worry about molecules. So can you see just going through this list of stuff that they give you and deciding what they are? But if you do this first, it actually makes your life easy when you go. People think sometimes it's a waste of time. But if you go and look at the questions confuse you sometimes. So if you go and you label each of the substances first, then you know it's a metal. So don't think about it when I ask for nonpolar or anything else because you know now already that it's a metal. So you don't have to worry when you see the questions. So now they can ask you anything. They can ask you, okay, which of these will form non-polar molecules? Yeah, Br2, yes. HCl is covalent because it is sharing, but is it polar or not? It's polar, yes. What about I2? Yes. Then let's look at our other molecules. Yeah, HF, would that be polar or non-polar? Okay. And then the other one we have is NCl3. Okay, so these what is the electronegativity of N? Okay, but now be careful. What are you looking at? Are you looking at molecules or are you looking at bonds? When you're saying 3 and 3, you're looking at the difference in electronegativity. Has that got to do with bond or has it got to do with molecule? It's a bond. When they ask you for a nonpolar molecule, you have to look at symmetry. Yeah. So tell me, how many electrons for N? One, two, three, four, five. Even if you just draw the N, you can already see what are these two negatives going to do with these one negatives. Exactly. So that, because they just have stronger force. So because they're two negatives and these are one negative. So the Cl will sit here and sit here and sit here. So is it symmetrical? So what type of molecule will NCl be? I almost wrote nonpolar. Yes, it's going to be polar. It's a polar molecule. Okay, so still, it's only these two. But now, if they ask you, let's just do that immediately. If they now ask you for non-polar covalent bonds, now you see the word bond. Now go and look at your substances and tell me which ones have non-polar covalent bonds. Good, good. Okay, so I and I will have a non-polar covalent bond, yes. Good. It's bromine. It's in group seven somewhere. It's group seven underneath. Good. All the diatomics will always be nonpolar. Mm. And then the last one. Okay. So can you see, even though it was a polar molecule, it's got nonpolar bonds. Okay. So this is the most important thing of the day, actually. I know we're out of time. That when they ask you for a bond, you look at the difference in electronegativity. When they ask you for a molecule polarity, so bond polarity, you look at the difference in electronegativity. Molecule polarity, you look at the symmetry. Okay, that is very, very important because that's the only thing you're still getting confused with.